stealth technology, the internet, GPS in the palm of your hand, autonomous operation.
Technology is a driver of our times. Since its founding in 1958 in the midst of the Cold War, DARPA, the Defense Advanced Research Projects Agency, has been a driver of technology. Welcome to Voices from DARPA, a window onto DARPA's core of program managers. Their job, to redefine what is possible. My name is Ivan Amato, and I'm your DARPA host. And today I'm pleased to have with me in the studio Lindsey Maillard, a program manager in DARPA's Tactical Technology Office, where since 2014 she has been running the intriguingly named Space Surveillance Telescope, or SST, program. Welcome, Lindsey, to Voices from DARPA.
Thank you so much for having me. I'm really excited to be here.
Well, I'm excited to have you. And before we dive in and talk about the Space Surveillance Telescope, which packs some really amazing technology that I'm eager to hear about, let's talk a little bit about you. What I'd like to know is something about your background and interests and how you became a program manager at DARPA.
Sure. So a while ago, I actually started as a photography major at the University of Michigan, which you might think is a little bit odd start for a scientist. I was always inspired by these images I would see in astronomy magazine. And at that time, I thought, oh, that means I should be a photography major. But after learning a little bit more my time there, I drifted over to aerospace engineering. I got my undergraduate degree in aerospace engineering there and a master's as well. And I went on to Purdue, where I did some graduate work that enabled a NASA mission called the Terrestrial Planet Finder, which was a new design for a space-based telescope. After that, I had some work I did in policy and actually met a fellow program manager here at DARPA who introduced me to how DARPA works and the DARPA programs, which is very exciting to me. And that's how I ended up at DARPA.
And before we do really talk about the advanced technologies that come together into this tool, the Space Surveillance Telescope, maybe you can talk to us a little bit about the problem that really beckoned, that screamed for something like an SST. And what I'm referring to here is the kind of relentless growth of both, I guess, human-made and cosmos-made debris. So I guess since really the beginning of the space age.
Yeah, absolutely. I mean, our use of space is becoming increasingly critical to daily life. I think a lot of people don't know when space is even involved really anymore. And in order to do that, we are launching increasing numbers of man-made objects into space. There are tens of thousands of these objects in space right now. And so we have to be very careful that they don't come near each other and sometimes even collide with each other. And on top of that, we also have debris in space, some from man-made objects, but also just natural objects. SST is really focused on tracking and identifying debris and objects in an orbit called geosynchronous orbit. That's about 22,000 miles above the Earth, so really far away.
Right, and that differs from LEO, right, which is low Earth orbit, and that's where a lot of satellites are there as well, right?
That's absolutely right.
Mm-hmm.
LEO's much closer, so it's a little easier to see objects there. GEO has a volume of tens of thousands of oceans, so not only is it far away, it's gigantic. And so building a telescope that can handle both of those challenges, seeing things very far away over a very wide area, is really what SST is best at.
Okay, I love that kind of image you just gave us with all of these oceans above that need to be looked at and monitored. So, that sounds to me like you need some oh wow technology, and maybe this is a good time for you to talk about those really advanced and unique technologies that you've helped nurture to come together into this remarkable instrument.
Yeah, absolutely. So when you think about a digital camera that you have at home, when you use your zoom lens, you see the field of view on your camera narrow in on the thing that you're looking at as you get closer. And that is how a traditional telescope works. As you change the design, the field of view narrows. With SST, we actually had a unique optical design where we use a curved focal plane. So again, thinking back to your digital camera, there is a small focal plane in your camera called a CCD.
And that stands for Charge Coupled Device, if I recall.
You got it.
Most of us know it just as the acronym CCD.
Thank you. Well, the way SST obtains that very, very wide field of view, but still relatively very high resolution, is actually instead of having a flat CCD or a flat focal plane, it is curved. And SST had the first working curved focal design that we know of in the world.
And what's so special about the curved format versus a flat one?
So the curved format allows you to actually focus the light a little bit better towards the edges of the CCD itself. It's also very, very challenging to build. In fact, MIT Lincoln Labs, who built the focal plane, had to come up with a completely new process and able to enable that curvature over the plane. Right,
and for those who might not know, the Lincoln Labs is a really fascinating place with a history that goes back really to World War II, with a task at that time to work on what really was some of the original radar technology, and it's been really involved in optics among other things ever since. So it's a really interesting partner in this case. What are some of the other technologies that have been really tough, DARPA-worthy type of technologies?
The processing power of this telescope is quite impressive, and the speed at which it can scan over the sky. And so we can actually view objects over 1/4 of the entire geobelt, or over, you can imagine it as 1/4 of the Earth, each night from New Mexico. And that is just an incredibly fast drivetrain on the telescope and requires incredibly fast processing. And those are two things that we also developed under the SST program.
Right. I mean, it's kind of an astounding volume to be thinking about as in the field of view of this instrument. And it's in a kind of an amazing perch, right? This is at the White Sands missile range in New Mexico, which I guess most people there know as Wismar, and it's on top of a fantastically named peak called Atom Peak. You've been there, so maybe you can just sort of paint us a little bit of a picture of what it's like to be there at night by the telescope. And while you're doing that, describe the telescope a little bit.
Sure. So the Atom Peak itself is very high and very dry, and in a very dark location. So you can stand up on the peak and actually see the sunset out over the range, which is beautiful. And you're also looking right over a site called Trinity Site. Trinity Site is actually where the United States exploded its first atomic weapon, which is kind of interesting to be standing on the edge of two areas where technology was developed. After sunset, again, it's incredibly dark. You can actually see the edge of the galaxy when you're standing up there. And after nightfall, you can walk inside the telescope dome. The facility itself looks like a very flat, square building with a giant dome on one side. And you get inside that dome, which is elevated even higher above Atom Peak, and they will open up the door of the telescope dome. And almost every time I've been there, the wind is just blowing, and it's freezing cold. But everyone wants to stay in that dome because it's just so neat to see the stars in the telescope moving. The telescope movement itself is completely silent. So you're just sitting there looking at the stars next to this instrument.
And Lindsay, give people a sense of the scale of it and how fast it's moving, because when you say this instrument is silent and I think about how big it is and how fast it's moving, it's almost impossible for me to think about.
Right. So the telescope itself weighs several tons, and it's sitting on top of many different gimbals. And what it's doing is the shape of the opening in the dome is rectangular. And so it starts at the top, and the telescope movement is going up and down, both up and down in a vertical and also across in a horizontal motion. And again, it can survey the entire sky, so 180 degrees around the dome in one single night. Again, that, volumes and volumes of ocean, a quarter of that in one night.
Right. And so it literally is, it's moving from one spot, taking a snapshot, moving to another, taking a snapshot. I heard that there's some thousands of horsepower worth of hydraulic piston and other moving elements that actually can bring it from one spot to the next. And yet the sound is something like, I've heard this, maybe you can correct it or you have another metaphor, about as loud as a microwave oven.
I think that's right. The only thing you can hear is the clicking of the shutter on the camera itself over the hum of a microwave oven.
Right. And then so when the shutter is open and it's gathering this light on that through that curved optical element that you talked about, so it can look at such a huge volume of space all at once, the light itself then is going onto, as I think you might have said, a sensor like that in our cell phones. Can you talk a little bit about that sensor plane?
Yeah, so I'll start with as the aperture is open, the light actually comes in and hits several different mirrors. It's a Mersenne-Schmidt optical train, and it's about a 3.6 meter mirror. So that gives you an idea of sort of how big the whole telescope is itself. It's several meters larger than that. And so the light will come in and bounce through that mirror and actually be focused onto that curved focal plane. Where the light hits the materials in that focal plane, and that turns them into an electrical signal, which is then transferred into what we would think of as pixels. Based on the strength of the electrical signal, you're either seeing a brighter or a fainter pixel. The longer the telescope is open and looking at a specific place in the sky, the fainter the object you might be able to see, just like if you were doing it at home with your digital camera.
Okay, so now I'm imagining the camera, it's staring out to geosynchronous altitudes, roughly, 22,000 miles above our heads there, and it's picking out perhaps thousands, at one time, thousands of even softball-sized objects. Is that right?
Yeah, that's about right. Maybe the size of a whiskey bottle.
And if we focused in on one of those objects, with the whiskey bottle you just said, now I'm wondering if there really are whiskey bottles whirling around in orbit.
One can only guess, right? We have had astronauts up there.
So let's assume it's not a whiskey bottle, but it's some other kind of debris. How many pixels would that single object occupy on the sensor of the SST?
Sure, so it would be very few. So SST cannot actually take what we would think of as an image of something in geo. What SST does is really see dots and streaks. So it is not resolved imagery of an object in geo, but really an indication of where that object is and how it's moving.
Okay, and that's really all important, right? You really want to know the trajectory, because then you can map that trajectory onto the trajectories of all the satellites that are out there, whether it's for DoD or other entities, and you can then sort of calculate where there might be an unwanted intersection of those trajectories, right?
Yes, that's absolutely right. And I'll also add that primary user of the telescope right now is actually NASA. We've partnered with NASA to try to identify and catalog new near-Earth objects. And SST is actually prolific at finding what we call these NEOs. Primarily asteroids and comets are what we're looking at.
Right. So that's been sort of in the test-out phase in these earlier kind of years in a way. It had its first light in 2011, if I recall my reading. Is that when it first went on top of Adam Peak? Or was that somewhere else?
No, that was on Adam Peak.
Okay, and so since then, can you give a sense of the catalog of observations that SST has made?
Since then, we've worked, like I mentioned, with NASA to look at objects, near-Earth objects, asteroids and comets. We've also taken some images of nebula and supernova, also for our partners at NASA. Work very closely with the United States Air Force. For the Air Force, we are observing very faint objects in geosynchronous orbit and providing them information on that. And that could be anything from a piece of debris to a small satellite. We also work quite a bit on developing what we call debris models. So no telescope is strong enough to see every piece of debris in space. And so what we do is we make estimates about where that debris might be based on what we know. So SST can see many more objects than other telescopes. And so we've been using our measurements to help develop models for what we think the reality of the debris is up in geo.
Okay, now you mentioned many more telescopes, and that made me think of the larger context here, which is the larger sort of space surveillance network.
Sure. So the United States Air Force operates, we call it the SSN. Everything has to have an acronym, the Space Surveillance Network. And there are several different types of optical and radar sensors in that network. SST is currently not one of those sensors, even though we do provide data on an ad hoc basis to the Air Force. But very shortly, it is going to become one of the sensors in that network. SST is going to be transitioning over to Air Force use. Actually very soon, on October 18th of this year.
That is an important kind of success for DARPA. when we think of what we're trying to do here is, develop technologies to further the cause of national security, we really do want this sort of transition ultimately to happen. We do a lot of high-risk kinds of technology development, so the transition doesn't always happen, but here is a case where it is. So can you talk to me about this Baton Handoff, right, and kind of where we are now so that we can make this handoff to the Air Force, and then perhaps also take us forward through the sequence of events that will occur over the next few years?
Sure. So you mentioned SST had first light in 2011. It was a demonstration system. That's what we developed.
But I'm just going to interrupt because for those who don't know, first light is just this wonderfully poetic term in the telescope community, which really refers to that moment when all of the conception is over and the development and the building, and you finally open up this wonderful instrument to observation, and you desperately want to see what that first observation is, and that's often referred to as first light. So sorry to interrupt, but that was in February of 2011, the first light for SST.
Yes, thank you. So at that time, it was a demonstration system, and here at DARPA, we try to really push beyond the state-of-the-art, revolutionary technology. And sometimes you don't always get it perfect the first time. And so with the camera that we had in there in 2011, we realized that there were some improvements that could be made. And so over the past year or so, we've been developing a new replacement camera for the one that exists there today. So we finished the installation of that new camera and had, again, first light on August 18th of this year. And we're currently demonstrating the improved capability of SST. Once that demonstration is done, and we're really certain that the technology is complete, we are just really excited to give this to the U.S. Air Force. It represents an order of magnitude increase in capability from what they're able to see now with their existing optical sensors. And so we are very excited to be able to give them that capability and have that actually run into operational use.
Right. So the Air Force will officially take stewardship of SST in an official ceremony that will be happening up on Adam Peak in New Mexico. What's going to happen after that?
After that, we are actually going to be, we being the United States, are actually going to be moving the telescope to Australia. We have signed...
Halfway around the planet.
Yes, not an easy task for a very large telescope. In 2013, the Secretary of Defense and also the Minister of Defense in Australia signed an agreement to actually move the telescope from White Sands Missile Range to Harold E. Holt Naval Air Station in Western Australia. And so once we complete the technology, demonstrate it, and transition it to the Air Force is going to continue to work with our Australian partners to physically move it over to Western Australia. And that will be happening over the next maybe 2 years.
Right. Now that sounds like an enormous project, probably worth its own engineering story. So why take the great pains to move this telescope a half planet away?
I completely agree. The movement is potentially a DARPA hard problem in and of itself. The reason to do it is because that is a part of the world that we're very interested in observing what's going on up in geosynchronous orbit. We have a lot of very important satellites in that area to include communication. And also it represents a great partnership with our Australian allies. It's for really those two reasons why we want to move it there.
We've covered a fair amount for the time that we have about the Space Surveillance Telescope. Is there a question that you really wish I would have asked here that I did not? And if so, you get to ask it now and answer it.
Okay. Well, maybe not a question, but I have a statement. My whole life, I've been interested in sort of looking beyond, what we can really see. And I think it's inspiring to work on an instrument that lets us see other galaxies. It makes it so real in a way. It's one thing to look sort of at a picture in a magazine, and it's another to be working with an instrument that can actually image a nebula and a supernova. So for me, working on the program has been inspiring, not only from a science perspective, but also because we get to contribute to a very important mission for the Air Force.
Lindsay, you're at a place, DARPA, which is kind of all about reimagining what is possible and actually taking steps to change or to take what might previously have been considered impossible and making it possible. So in a way, it's a place that's trying to make science fiction nonfiction. I'm just wondering if you have some what are now fictional technologies in mind that you think ought to be real.
So I have a couple. One is the Universal Translator. I think it might have been on the Star Trek series. That is a technology, or perhaps a superpower that I absolutely wish that we had. I think the other one is to travel beyond the stars. Perhaps that's that one you could have guessed. It's not enough for me to just look. I wish we could go there.
That's a good place to end, I think. So, Lindsay, I just want to thank you for this great conversation.
Thank you very much.
Glad you were here. And thanks, listeners, for sharing this time with us. I hope you join us again for the next Voices from DARPA. For more information about DARPA, the program managers, and the breakthrough technologies they are developing, visit us online at darpa.mil.